In this video, I want to talk about the integrating amplifier. So we have seen the interesting relationship that we had between the voltage and current of inductors and capacitors. So let me just quickly repeat them. So for the inductor, the voltage across the inductor was L di over dt. So basically the voltage across the inductor was in proportion with the derivative of its current with respect to time. For the capacitors, the current that went through a capacitor was C dV over dt, or basically the current was in proportion with the derivative of the voltage with respect to time. So based on these equations, we can design circuits using op-amps with interesting functionalities. So here you can see an example of an integrating amplifier. So if you look closely, you see that it is very similar in design to the inverting amplifier that we have seen before. So let me just quickly draw that as a reminder for what we have seen before. So this one is also connected to the ground and the proper signs, and we had RF and RS, and this one was VS, and this one was positive, negative VO. So we know from the analysis that we had for op-amps, VO is actually negative RF over RS multiplied by VS. So this was the general equation for the relationship between the output voltage and the input voltage of this inverting amplifier. But now instead of this resistor, we have a capacitor. But the procedure for solving this circuit and finding the equation is still the same. We again write the KCL for the inverting and non-inverting terminals of the op-amp. So if you remember, we had two major constraints for op-amps. One was the voltage at the non-inverting input and the voltage at the inverting input. They were the same, and that was because of the very high gain that we have for the op-amp. And the other constraint was with regard to the current of the op-amp. The current that went through the non-inverting input was equal to the current that went through the inverting input, and they were both zero, and that was because of the high input resistance that we had for the op-amp. So based on these two constraints, we can start solving this circuit. So what we do is that we write the KCL for this node, and we have IN here and we have IP here. So we know that IN is 0. So basically for this node, we have only IS entering and IF also entering. So that means that the sum of these two currents needs to be 0 because these two are entering the node while IN is leaving. So IN is equal IF plus IS, but since IN is 0, that means IF plus IS equals 0. So this is the first equation that we have. But how can we find the values for IS and IF? For that, we need to know what is the voltage at the inverting input. But we know from the voltage constraint that Vp, or the voltage at the non-inverting input, is the same as the voltage at the inverting input. So we see that the non-inverting input of the op-amp is directly connected to the ground, so that means Vp is 0. So if Vp is 0, that makes Vn to be 0 as well. So Is is going to be Vs divided by Rs, because this is practically ground, and IF, the current that goes through the capacitor, is going to be CF, basically the feedback capacitor, multiplied by the derivative of the output voltage with respect to time. Again, this you can say practically is connected to the ground. So the current that goes through the capacitor is in proportion with CF multiplied by the derivative of the voltage across the capacitor over time. So now we can simply replace these equations here, and if we do that, what we have is dVO over dt equals negative 1 over our SCF multiplied by Vs. So on the left side we only have VO, on the right side we have Vs. So now to be able to solve this differential equation, we need to multiply both sides by the differential time. So we multiply this by dt and also this by dt. So these two would cancel each other out. And now on the left side we only have VO, and on the right side we only have time, and Vs is a known value for us. You have seen how I calculate this integral. We have VO, which is a function of time, equals negative 1 over Rs multiplied by Cf. Because this is a constant, you can take it out of the integral. Inside the integral, since we actually don't know what is the exact function of Vs, we have the integral of Vs from time t0 to t, and then dy, and this y is basically the same variable as t, but I have changed it to avoid the confusion. It is only for representation purposes, and it doesn't affect the calculations. And then this would be added with the initial value for the voltage of the capacitor. Remember, capacitor can store energy in the form of initial voltage. So that's why we have this additive term too. So as you can see, the relationship between the output voltage and the input voltage Vs are calculated based on the integral. So that is what this circuit, why this circuit is called an integrating amplifier. We have this gain multiplied by the integral of Vs, not the actual Vs. So let's just take a look at one example of how this thing works. And for this example, I assume that VO at time t0 equals 0. So let's just say we have this waveform for Vs between time 0 and t1. The value is Vm, a constant value, and between time t1 and 2t1, the voltage for Vs is negative Vm, again a constant value. So this is usually what is called as a square wave, because the shape resembles a square. If we pass this signal to the circuit as the input, since the relationship for the output voltage is a gain multiplied by the integral of the input voltage, this is the output that we have. It's a triangle wave. Of course, since we have this negative sign, the wave is reflected, right? So it is on the negative side of the voltage, so the values are negative. But nonetheless, what we have is we have an equation that is basically the integral of this square wave. So during this time, as the time passes, we basically are having a positive value for the integral, or the area under the curve. And this area grows when we go from t0 to t1. But after t1, the area under the curve starts to decrease because we have this positive part and this negative part. So that's why we have these two linear shapes from t equals 0 to t1 and t equals t1 to 2t1. The reason that the sign is reversed because we have a negative sign as a result of the op-amp circuit, which, as I said before, that resembles the inverting amplifier that we had. But at the end of the day, we were able to create a circuit that calculates the integral of a signal for us. In this video, we'll learn how we can design and analyze integrating amplifiers using capacitors and operational amplifiers.